Hello everyone. Today inshallah we will go through partial derivatives as this is the second part of our course inshallah. So let's start this bunch of lectures. I believe at the time being we will be able to finish both partial derivatives and the start of directional and the higher order derivatives today inshallah. We will need the differentiability in R and Rn for the next lecture inshallah. When it needs to be. Of course, all of our course references, notes, and everything, you will find them on Moodle. As usual, usually like to remind you all about this, you will have to go to Moodle. You have webs, you have unlimited resources, and of course, the recorded lectures, you will find them on my YouTube. In this session, I will try to cover the following topics. We will try to go through definitions and relations, partial derivatives in Rn, the gradient vector and the Jacobian matrix and what the difference between them, when to use them, okay? So I will start with the total derivative. If you want to study the idea about derivative is measuring the rate of the change of the output variable relative to the change in the input variable. If we are talking from R to R or single valued functions in one variable, then you will do total derivative. You don't need partial derivatives. The partial derivatives will start to appear with the gradient or with the Jacobian once you are starting to deal with either the other two situations in functions. Function in several variables or vector valued functions, okay? But for the total derivative, the definition is really very clear. All you have to do is to get the ratio between the change of the output relative to the input. So this is the slope of f dash at A, or the derivative at a certain point. It is the slope of tangent line to the graph at this point, which is usually the rise over run. So I will get the difference between the output, which is f of x minus f of a, divided by the difference in the input, which is x minus a, okay? So simply, it will be reported at this case. F dash of a, limit x tends to a, for f of x minus f of a divided by x minus a. And they can be reformulated to the standard limit of the differential law or the derivative by the first principle, which is limit a plus h minus f of a divided by h. Of course, this is the start of everything from the derivative. Going from this part, f of x plus h minus f of x divided by h. This way you will be able to get the derivatives of the main functions, of the principal functions, okay? That's the main level. Okay, very good. An example on this, if I want to get, for example, the derivative of f of x equal to x at x equal to 1. This is very, very simple. All I have to do is to apply this equation or to apply this limit. So f dash at 1 will equal to the value of the function at 1 plus h minus the value of the function at 1 divided by h. All I have to do is to just make a substitution in the value of the function. What's the value of the function, Omar? It's f of x. So I will replace x by 1 plus h. Then I will replace x with 1 because I am seeking the derivative at 1. So simply it's going to be ln 1 plus h minus ln 1 over h. Okay, let's simplify it. I know that when you substitute with h tends to 0, this is not going to be defined because simply it's going to be ln 1 minus ln 1 over, which is 0 over 0. But yes, you are right. Ln 1 is equal to 0, so this part disappears. And if you make the substitution of h equal to 0, you will have ln 1 also, which is 0, so we are still in this problem. But I can do something very, very nice. Trying to expand ln 1 plus h using one of the expansion methods. One of the famous expansion methods is Maclaurin expansion. So if I want, and we will go through this in the coming lectures, inshallah. So if I want to make a Maclaurin expansion for ln 1 plus h, this is going to be the result. It's going to be h minus h squared over 2 plus h cubed over 3 minus h to the power 4 over 4 and so on. If I took this value and divided by h, ya Omar, I can take h as a common from the denominator. So if you remark, if I took this value and divided by h, this is what I did in here. This is the expansion over h. Try to take h from all the denominator as a common. You will have h times 1 minus h over 2, h squared over 3 minus h cubed over 4. Then I will eliminate these two values together. This is the expansion that I have. Now apply the limit. The limit h tends to 0. Which means I will substitute with all of these values h equal to 0. So that's the limit of f-1 at limit h tends to 0 is going to equal to 1, which is the value of the derivative of this function at 1. Since we already know the laws of how to find the derivative of ln x, if I want to check this result, what's the derivative of ln x, Omar? Do you remember?
Ln x,
1 over x. Yes, you are right. Okay, so the derivative of f of x, it's 1 over x. So at 1, it's going to be 1 over 1, which is exactly the same result that you reached. Okay. Once more, I want to get the derivative of this function at 0. The function is given by x minus 2 to the square root of x squared. So all I have to do, once more, is to apply the law. What's the law? The law states that f dash at 0 will equal to the limit x equal to 0, I'm sorry, h tends to 0 for 0 plus h minus f at 0 divided by h. That's the limit that we are going to use. So all I have to do is to make this substitution. But don't forget, f of x at this time, it is this function. So I will replace x by 0 plus h. And I will replace x squared by 0 plus h. So all I have to do, in order to evaluate the value of the derivative at 0, is to make the substitution of f at 0 plus h minus f at 0 divided by h. All I have to do is to make this substitution. So once more, I will replace x by 0 plus h. And this x will be replaced also by 0 plus h, minus the value of this function at 0. The value of this function at 0, if you like, to get f at 0, it's going to be 0 minus 2 to the square root of 0, which is 0. So that's the definition of the function is going to equal to 0. This is why you have the substitution of 0 plus h, which is this part, minus the value of the function at 0, which is 0. Now let's simplify it a little bit. Of course, 0 plus h minus 2 will leave you with h minus 2 times the root of h squared. Before we go further, if you remark, if I took a square root for h squared, yes, you are right. It's going to be positive or negative h. So if it is positive h, the result will be h minus 2h over h. And to be positive, it means I will take h tends to all positive, which means I'm approaching the origin, but from the right direction. So if you are coming from the right direction, the value of this root will be the positive value. In this case, I will eliminate these two guys together, and the substitution will leave you with negative 2. Okay, yes, you are right. Also, x will approach from the left side. If it is approaching from the left side, so in this direction, instead of having positive h, it's going to be negative h. Once more, I will eliminate both of them together, as you can see. And in this case, you will have negative 2. In this case, the limit doesn't exist, because simply the limit from the left is different than the limit from the right. So once these two limits are not equal to each other, this means that there is no value for the derivative at 0. And that's usually a question you can find in exams or something once he is asking you to to speculate the value of certain derivative and so on. Okay, people applied this law, which is the law of the principal differentiation using the first principles, and the results come for the following. If I want to have total derivative, and once more, Omar, we use total derivative in the case of functions running from R to R. So it's a single variant function from R to R. Okay, I will use dy by dx. Of course, derivative rules are fixed, and I'm sure that you know and you memorize some of them. So if I have f and I have f of dash, and I can relate the basic ones or the basic ideas, the basic set of laws, and you'll find all of this in the PDF that I already sent. A derivative of k is going to equal to 0. If you have u plus or negative plus or minus v, and you make the derivative, it's going to be u dash plus or minus v dash, as you can see. Okay, if I have k times u, with k is a constant usually is taken outside the derivative sign. This is why it's ku dash. Of course, you remember the multiplication rule. If you have two functions multiplied in each other, I will get the derivative of the first function times the second, plus the derivative of the second function times the first. If I have two functions divided in each other, then the derivative law states that we will get square of the denominator, differentiating the numerator times the denominator, minus vice versa. This is exactly what happened. Also, some of the very famous functions, which is in case of having u to the power of n, if I want to differentiate, it's going to be simply n times u n to the power minus 1 times u dash. If I have e to the power of u, then the derivative, it's going to be same function times the derivative of the power. So it's going to be e to the power of u times u dash. If I have len u, like len x, it's going to be 1 over u times u dash. Okay? Those are the general derivative laws. If I have a to the power of u, then its derivative is going to be the same function, len a times u dash. You will have 3 parts. If you have log u to base a, it's going to be u dash over len a times u, as you can see. Those are the basic bunch of derivative rules that we can use in most of our problems. Of course, there is another types of functions, like the trigonometric functions, like the hypergeometric functions, but at the time being, we are not interested in them. We're just interested in this set of functions. So simply, if I want to differentiate e to the power of 3x minus 1, according to the previous relation, all I have to do is to find f dash of x, which is the total derivative, f dash of x, is going to equal to same function, which is e to the power of 3x minus 1 times the derivative of the power, which is 3, as you can see. If I want to differentiate anything, you can apply the previous laws to plenty of problems. So, for example, if f of x was like the root of len of x plus x squared plus y squared, and I want to differentiate, it's not going to be a big deal. Of course, all I have to do first is to raise the power, so it's going to be len of x plus x squared plus, I'm sorry, this is, let this guy be 4, because we are talking about a function from R to R still at the time being. So it's going to be x squared plus 4 to the power of half. So y dash or f dash of x is going to equal to. Start differentiating. So I will differentiate first the power, which is going to be 1 over 2 times. I will subtract 1 from the power. So the function will be ln of x plus x squared plus 4 to the power of negative half times the derivative of the function inside the bracket, which is 1 over x plus 2x, as you can see. It's just a direct application of the previous law. Of course, this is an application of f once it is u to the power of n, then f dash will be n times un minus 1 times u dash. This is exactly what we applied in this case. Also, another problem, if you like, I can go for problems like this. If I have f, which is ln over x squared plus a root over x plus 1 over x, for example, I can find f dash directly. So f dash of this function is going to equal to 1 over the argument of the logarithmic function. So it's a 1 over x squared plus a root of x plus 1 over x. Then it will be times the derivative of the argument. So simply it will be times the derivative of x squared, which is 2x, then plus the derivative of root x, which is 1 over 2 root x, as you know. 1 over x, it is x to the power of negative 1. So if I want to differentiate, it's going to also be some. All I have to do is put it negative 1, then subtracting 1 from the power, which is going to be negative x to the power of negative 2. That's the derivative of, or the total derivative. I want you to remember that we are using total derivative in case of functions running from R to R, single valued functions. This is what's called a total derivative, differentiating y with respect to x, or I can symbolize it by putting f dash of x, as you can see. This is mainly a bunch of problems among unlimited number of ideas, just playing the derivative rules. So once more, as you can see, all of these problems and the plenty of ideas related to the main laws that we saw in the previous lecture, in the previous slide, can be applied. So once more, for differentiating the function which is f of x e to the power of 3x minus 1, the derivative is going to be simply putting once more e to the power of 3x minus 1 times the derivative of the power, which is going to be 3. This is what I was saying. There is plenty of problems and examples can be done as we go through our course. But at the time being, I would like to introduce the composite function as we will need it down the road. So I will start with introducing the composite functions, as you will see. Okay, then we will move back to more challenging topics in the case of Rn into R, or functions in several variables. But for the time being, I will take the advantage of letting you know how to make a derivative in the case of composite functions. And down the road, we will hit this one. Okay, and we already partially using these rules. Okay, for composite functions, you know that I can write f after g, or f composite g, which means f of g of x. By the idea, if I want to define the derivative of this function, بص يا عمر, if I want to find the derivative of this function, all I have to do, in order to get f composite g derivative, it's going to equal to first the derivative of f, which is f dash of g of x, then times the derivative of the inner function, which is g dash. So what I'm doing is I'm differentiating the outer function, then times the derivative of the inner function. And this can be applied to the same problem that we were in. So if I want to differentiate, for example, f of x is equal to e to the power of 3x squared minus 1, for example, okay? I have two functions in each other. I can relate this problem to exactly this law. The outer function is an exponential function. The derivative of the exponential function is going to be e to the power of 3 over x squared minus 1 times the derivative of the inner function, which is 3x squared minus 1. Are you with me, Omar? Which is going to be a 6 over x. So actually, you are doing the same exact steps. But sometimes it will be confusing, especially if you put everything all together, like the problems that I will get you to see. So once more, here we go. If you want to differentiate d by dx for f g of x, all you have to do is to get the derivative of the outer function times the derivative of the inner function. It's really simple. Okay, the concept is very important and we usually use it in general in derivatives. That's what I was saying to you. So f g of x is a composite function, f dash is the derivative of the outer function, j dash is the derivative of the inner function. That's the terminology that you can see in this part. This is also the composition means you have f of x which is, or g, which is running from Rn into Rn as a generalization of the composition. And you have another function which is f running from Rn into Rb or something. This is f. This symbolization is actually f as composite g of x. This is the terminology for this case. So mainly what's happening to Omar is G is applied. And G is going to be applied from Rn into Rn as a generalization in any dimension. And then after you have your output value, it's going to be the input of the second function, which is f. So this is actually what's happening. It's already explained in this paragraph. I'm not going to lose time, more time in this slide. I believe it is, as I told you, this is the idea of having f composite g, which means you will run first g of x, and then the output of g is going to be the input of f to transfer it to the other dimension. Also, this terminology is the terminologies that we used in linear algebra for understanding how to move between composite functions and composite linear transformations. Okay, just a second. Where is my... So once more, H dash, this is the rule that we are using. Let me give you this problem. It's very, very nice problem, but it needs concentration. Okay, I want you to get the derivative of b after q at 2 and the q after b, okay, at 2 also. Sorry, that's a typo, at 2. Where b of x is root of x and the q of x is 2x plus 5 over x plus 1. So if I want to do this, I will start with evaluating, because I know that this relation is gonna be like this: b of q of x. So if I want to get the derivative, I will get the derivative as follows. This means b dash will equal to, or if I want to find the derivative of this composition, it's going to be b dash q of x times q dash of x. And since we are evaluating at 2, so I need this value to be 2 and that value to be 2. This is the plan. This is what we are going to do. So as you remark, we need to find the q dash at 2. And we need to find q at 2. So I will start from this part. So q at 2 will equal to, I will make a substitution by 2. So 2 times 2 is going to be 4, 4 plus 5 is going to be a 9, divided by 2 minus 1, which is 1. That's the value of q at 2. Then I will get the value of b at 2. So b at 2 also, it's going to be a root 2. Let's differentiate both q and p. If you differentiate b, it's going to be b dash of x, which is gonna be 1 over 2 root of x. So if you want to get b dash at 2, it's gonna be 1 over 2 root 2. Are you with me? Similar manner, can you differentiate this guy? Can you differentiate this function? It's very, very simple. It's u over phi. So if I want to get q dash of x will equal to square the denominator, so it's an x minus 1 to the power of 2. Differentiate the denominator, which is going to be 2. So it's going to be 2 times x minus 1 minus. Differentiate the denominator, which is 1, times the denominator, which is 2x
plus 5 as you can see. Now start to simplify things. So it's gonna be x minus 1 to the power of 2. And in this case you will have 2 of x minus 2 minus 2 of x minus 5. Those guys will eat each other and the result will be negative 7. So if I want to get q dash at 2, all I have to do is to substitute by, instead of x by 2, so it's gonna be a negative of a 7 divided by 1, which means negative 7. Now I have these values with me. I will get back once more to my problem. If I want to find b composite q dash at 2, it means I will have to get b dash first, but at q2, then times q dash at 2. This guy I already have, which is negative 7. This is negative 7. But the problem is, I will have to evaluate q at 2. Let's see what's the value. Q at 2 is equal to 9. Am I right? So I will start substituting, getting b dash at 9. So if I want to get b dash at 9, all I have to do is to, in order to get b dash at 9, it's going to be 1 over 2 over root 9, which is going to be 1 over 6. So all of this will be negative 7 times 1 over 6. That's the result. So if you have a multiple choice problem, Mr. Omar, he will ask you to choose the right answer for b composite q dash of 2. You will have to do all these steps, and that's going to be the right choice. If I want to get q composite b, it will be the same. So if I want to get q composite b dash at 2, it will be getting the first q dash of b at 2, then times the derivative of b dash at 2. If you remark, b dash at 2, we already have it. b dash at 2, okay, where is b dash? Yes, here we go. b dash at 2, it's gonna be 1 over 2 root 2 times. The problem now is I want to get q dash, but at the value of b at the number 2. The value of b at 2 is root 2. So I want to get q dash at root 2. That's q dash. That's q dash. So all I have to do is to make a substitution. So it's going to be a negative of a 7 divided by root 2 minus 1. Are you with me? Are you with me? So just rearrange it. So it's going to be negative of a 7 divided by 2 root 2 times root 2 minus 1. That's the right choice if you are getting q composite. As you can see, it's just a simple application for the steps. So I was started by evaluating everything, but of course I memorize the law and I know how to apply it. Okay, Omar? Once more, let's go through it once more. This problem is really very important as it transfers to you how we do the composition of the derivative of the composite functions in details. So once more, this is b dash of x, as you can see, 1 over 2 root of x. This is q dash, which is negative 7 over q minus 1 to the power of 2. Let me get the values of b at 2, q at 2, b dash at 2, q dash at 2. It's a direct substitution in the values. Then I will start substituting, getting b dash, but the inside function is q of t of 2. This is the value at 9. And times q dash of 2, it's one of those guys. So it's going to come up to negative 7 over 6 as we saw. And also, if I want to get q composite b dash of x, all I have to do is to get first q dash at the value of b of x times b dash of x. I already have b dash at 2. And the first part, which is q dash at root of x. So this is the result that you have. If I want to evaluate at 2, so all of these values are 2. If I want to evaluate x, it's going to be x. Okay.
Also, the concept, as I told you, of the composite functions, like this guy, sine of an x squared. I have an outer function which is sine, and the inner function which is x squared. So if I want to differentiate simply, it's gonna be sine over u with u equal to x squared. Differentiating the outer sine, it's gonna be cosine. So if I want to differentiate this guy once more, it's reversible. It's gonna be differentiating the outer sine, which is gonna be cosine, of the inner function x squared times the derivative of the inner function, which is 2x. That's the derivative of this. If I want to treat it as a composite function, it's gonna be exactly as I told you, cosine x squared times 2x. So it's a 2x cosine x squared. Also, if I have this problem, which is e to the power of x cubed plus 5x, also I will differentiate the outer function times the derivative of the inner function. The derivative of the outer function, it is the function by itself, which is ex cubed plus 5x, times the derivative of the inner function, which is 3x squared plus 5, as you can see. In a similar manner, that's another problem. I want to differentiate tan over root of x plus 1. I will differentiate first the outer function. The derivative of tan, yes, you are right, 6 squared, times the inner, times the derivative of the inner function, which is 1 over 2 root of xy, of x plus 1. That's exactly the same. D by dx over root of x plus 1, which is 1 over 2 root of x plus 1. And then I will multiply all together. So it's going to be second square of x plus 1 times 1 over 2 root of x plus 1. معايا سي عمر؟ قشطة. Okay, now I will talk about partial derivatives. Before going to partial derivatives, you know, yes, you are correct also, that we are using or dealing with partial derivatives in the case of functions running from Rn into R. In this case, I will use partial derivatives. So the total derivatives used when you are running from R into R. But the partial derivatives is in the case of running for several variables into one variable, Rn into R. Okay, a very good example on the partial derivatives is the functions in 2 dimensions. So if I have a function, and this is the x-axis and y-axis, I'm in R2, I can get simply the derivatives of this function with respect to x or with respect to y. So I'm determining the direction that I'm using in my derivative. So in these functions, which I have 2 variables as an input, and I want to make the derivative, I will have to signify for everyone. Am I making the derivative with respect to x or making the derivative with respect to y? This is really very important. Remark, it is exactly the same law. Can you remember the law that we were using? Yes, it's an f dash at a. Do you remember, Omar? Yes. Limit h tends to 0, which is f, am I right? Yes. A plus h minus f of a divided by h. This is the law once you are dealing with one variable. But if you are dealing with 2 variables, the shift that you are using, if I am differentiating with respect to x, the shift in x. But the y constant, the y remains constant. Are you with me? Okay, so it's an f of a plus h and b minus f of a and b, which is exactly like this guy, divided by h. But if I want to make the derivative with respect to y, in this case, the x direction will remain the same. But h will be added with the y direction. So it's going to be b plus h minus b, as you can see. It's a generalization of this law. Are you with me, Omar? Okay. Is it clear for you? Yes. Okay. If I'm dealing with function in 3 variables, it means that I will have a plus h, b, and c. And this is going to be f of a, b, c. And here also, it's going to be f of a, b plus h, and c. This is going to be a, b, c. If I want to get the derivative with respect to z, so it's going to be f of a, b, and then c plus h.
minus f of ABC divided by h and so on. So it's just a generalization of the rule. Of course, the derivative at a certain point, it will give you the derivative of the tangent at this point. So if you are dealing with a function in x and y as an input, this is going to be the shape of the tangent at certain point as you can see. Of course, that's the generalization that I'm telling you about. If I'm moving into Rn, so I have n variables, see, Rn into R, from Rn into R. In this case, remark Omar, I'm differentiating with respect to x sub I. So this is A1, A2, A3. Till you reach A sub I will add h minus the same function over h. That's the generalization of the law as you can see. Okay, let's try to get the derivative of this function, okay, around x and around y. If I want to, and I will evaluate around 0 and 0. So for the time being, A and B are zeros. So I'm getting in the direction of x, then in the direction of y. In order to get f sub x. So once more, if you forget the law, it's really very simple. The law states that the derivative f dash of x will equal to, that's the limit. Limit of what? Limit of x and y tends to 0. Or I can make the limit h tends to 0 for the function at 0 plus h and 0, because I'm moving in the x direction, minus f of 0 and 0 divided by h. This is f of x. But if I want to get f, but with respect to y, the derivative with respect to y, can you tell me, Omar? It's going to be a limit of h tends to 0. And in this case, this is your function. The x will remain the same, but I will add h on the y direction minus f 0 and 0 divided by h. Those are the main two laws in order to get the function in either in the x direction or in the y direction, as you will see. So those may be the main laws. So once more, this is going to be f